In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continue to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best, curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons, it captured the hearts and minds of generations back home on Earth. These are the probes that have gone the furthest that any human object has traveled. They are trailblazers and groundbreakers. It is their unique opportunity and their peril to travel beyond the reach of humanity. To capture images of things we have never seen before so close up, nor have we seen since. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered, time after time. So, you curious to see what they learned? I'm Alex McColgan, and you're watching Astrum. And in today's Supercut we'll cover everything you might ever want to know about the Voyager missions, from the probes themselves, their grand tour, to their impending, tragic finale. It's one of life's little ironies that it is not new, cutting-edge technology that is advancing our understanding most at the edge of our solar system, but old machines. They have an onboard computer with less memory than the one inside your car's key fob. To this day, they are still using 8-track magnetic tape from the 1970s, which makes them older than many of you sitting here watching this. Such is the conundrum of deep space exploration, where vast distances and extremely long travel times can mean that technology is antiquated by the time it has reached the most ambitious targets. Of course, Voyager 1 and 2 were not initially meant to travel all the way to interstellar space. They were instead built for a 5-year mission to explore Jupiter and Saturn and their larger moons, which was only possible thanks to a rare, once every 176 years planetary alignment. However, after completing all of its initial objectives on Jupiter and Saturn, the Voyager mission team added flybys of Uranus and Neptune to the probe's objectives. Later, these, too, were completed, so NASA announced the start of the even more ambitious Voyager interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. This final journey would take both probes off the ecliptic to unexplored parts of the solar system, such as the termination shock and the denser and hotter Helio sheath, before finally crossing the Heliopause into interstellar space. But how did these incredible machines manage to accomplish so much beyond the scope of their original mission? It all comes down to that old, but incredibly effective technology. NASA scientists made a number of forward-thinking design choices that allowed the probes to far exceed their initial objectives. To put it simply, they were built different. Here's how. Let's start with one of the most consequential decisions, the fuel source. Each probe is equipped with a long-lasting radioisotope thermoelectric generator which converts heat from the decaying plutonium-238 isotope into electric power. These generators were capable of producing 157 watts of electrical power upon takeoff, about enough to power a laptop and charge a mobile phone too. This might not sound like much, but was more than Voyager needed. While a radioisotope generator meant that power production was in constant decline, it would halve in strength every 87.7 years, it would still be enough power to keep the essentials on the probes running until at least 2025. This long-term fuel capacity was no. This rare alignment would not only allow the Voyagers to visit Neptune launched in 1977 with minimal force adjustment, but also give the probes a gravity assist from each of the 4 in 176-year alignment that had last occurred increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. However, this narrow window gave NASA a strict deadline. There wasn't enough time to plan follow-up missions, and the United States Congress wouldn't earmark enough funding for a longer expedition, like the Grand Tour NASA first proposed. So, what did Voyager's team do? They devised a series of engineering feats to optimize the probes for a potentially longer mission and fervently hoped that the funding would follow. Each of the Voyager probes is equipped with 11 scientific instruments. Most of them have redundancies in case of machine failure, which can be toggled on and off to conserve power. To adjust course and orientation, the probes are equipped with gyroscopes for stabilization, referencing instruments, and 16 hydrazine thrusters, including 8 backups. Backups, and good backups at that, were key to the Voyager probe's longevity. They proved to be vital as Voyager 2's main thrusters stopped working after 37 years. Its backup thrusters had to engage after 4 decades of idleness. And guess what? They worked perfectly, highlighting the excellent engineering that went into them. The Voyagers also have custom-built onboard computers, which are antiquated by today's standards but were cutting-edge in 1977. The probe's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem, which has fixed programs like fault detection and correction routines. Another key to its success lay in its computers. Each probe had a computer called the Attitude and Articulation Control Subsystem, and no, it doesn't scold the Voyagers when they get sassy. Attitude refers to the probe's orientations with respect to the Earth, without which their high-gain antennae would be unable to send or receive signals from NASA's deep space network. This is very important, as the probe's transmitters only have the wattage of a refrigerator light bulb, and at such immense distances, their radio signals become barely detectable whispers. To communicate with the Voyager team and vice versa, the probe's antennae must be facing the Earth, and the Deep Space Network must in turn know exactly where they are. Otherwise, they would be lost, like a needle in a 287 billion kilometers haystack. Each Voyager spacecraft has a 3.7-meter antenna for real-time transmission and an 8-track digital tape recorder capable of buffering 536 megabits for future transmission, enough to store 100 photographs. While this was a huge step up from the earlier Pioneer probes, which had no onboard data storage, it's still a fraction of what the smartphone in your pocket can store today. Despite these limitations, the DTRs were built to last. Otix, which manufactured them, claimed their DTRs could process over 4,000 kilometers of tape without taking visible wear and tear. They had to withstand the harshest environments imaginable and undergo rigors that had never before been tested. Yet, the Voyager DTRs performed without data loss or machine failure until they were finally taken offline to conserve power. Not bad for machines 12 years older than the World Wide Web. Durability was a chief concern during Voyager's planning. There are many unknowns in a mission of this magnitude. To get to Jupiter, both Voyagers would have to pass through the asteroid belt. Scientists once believed that this region would shred apart any spacecraft that tried to pass through it. However, Pioneers 10 and 11 had previously been able to pass through the asteroid belt, which emboldened Voyager's team to repeat the stunt. However, failure would have meant disaster before the probes had even reached their first target. Luckily, both probes